So in this lecture, I'll cover about the concept of backtracking, that is introduction, and as well as the recursive algorithms, and as well as the iterative algorithms which are involved in the backtracking concept. So when you consider about the backtracking, that is here the backtracking algorithm uses the depth first search. So the backtracking concept uses the concept of the depth first search, and when the algorithm begins to explore the solutions, the bounding function has been applied. So here you can observe using the concept of your the backtracking, the bounding function has been applied. And what is the objective of the bounding function? That is, within the bounding function, you're finding whether if you take this kind of the path, it leads to the solution or not. If it does not, based upon the constraints, if it does not satisfy the constraint, then backtrack. That kind of the criterion satisfaction problem. If it satisfies, then it can go to the next levels. If it is not, then we apply the bounding function. So here, if you consider any kind of the backtracking algorithm, the algorithm seeks a path to a feasible solution that includes some intermediate checkpoints. If the checkpoints do not lead to the viable solution, the problem can return to the checkpoints and take another path to find the solution. And similarly, backtracking can be applied only for the problems which admit the concept of the partial candidate solution. That is partial candidate solution, and relatively a quick test on whether this solution leads to the viable solution or not. It is useless, for example, for locating a given value in unordered table when it is applicable. However, the backtracking is often much faster than the brute force enumeration of all the complete candidates, since it can eliminate many candidates with the single test, rather than searching for whatever the possible solutions which are being present. Instead, you can go for a certain kind of the solutions which may lead to the final solution. So here, as I've explained in the concept of the constraints which include like explicit constraint, that is explicit constraints, and we have the implicit constraints. So explicit constraints, these are the rules which restrict each xi to take on values only from the given set. And implicit constraints, these are the rules which determine which of the tuples in the solution space satisfies the criterion functions. So the terminologies used in this kind of the method, like we have the first one, that is criterion function, and the next terminology used is the solution space, and the third one, that is problem state. The next one, that is solution states. Fifth one, state space tree. Answer states. The next one, that is live node, and we have e node. Next one, dead node. The 10th one, that is bounding function. And the 11th one, that is branch and bound is not being taken into the solution. So here, these are the terminologies which are being used in the context of the backtracking. So here the first criterion is the criterion function. So when you say about the criterion function, it is a function that is p of x1, x2, xn, which needs to be maximized or minimized for a given problem. Similarly, if you consider about the solution space, the solution space, all the tuples that satisfy the explicit constraints define a possible solution space for a particular instance, that is I, of the given problem. And coming to the problem state, that is each node in the tree organization defines a problem state. That is each node in the tree organization defines a problem state. And coming to the fourth one, that is solution states. These are the problems that states yes, for which the path from the root to the yes define a tuple in the solution space. And coming to the state space tree, that is if we need to represent the solution state space in the form of the tree, then the tree is referred as the state space tree. If you need to denote the solution in terms of the tree diagram, such kind of the tree diagram is called as the state space tree. Answer states, that is these solution states yes, for which the path from the root to yes defines a tuple which is a member of the set of this solution. That is, it satisfies the implicit constraints of the problem. And coming to the live node, that is live node is also live node, e node are being implemented. So coming to the live node, that is a node which has been generated and all of whose children have not yet been generated as the live node. I repeat, so a node which has been generated and all of whose children have not yet been generated is called as the live node. And e node, that is the live nodes whose children are currently being generated, is called as an e node, which is called as an node being expanded. The dead nodes, that is it is generated node that is either not to be expanded further or one for which all of its children have been generated. The bounding function, that is it will be used to kill the live nodes without generating all their children. And the applications of the backtracking concept, that is permutations of set of values, that is producing permutations of a set of values, parsing languages, and the next one, it can be used in games such as crosswords, 8 queens, word jumble words, and it can be used in combinatory and logic programming. Hamiltonian cycles, graph coloring problem. These are the some of the problems that can be solved using the concept of the backtracking. And coming to the video, that is in this lecture, as I mentioned about the brief introduction of the backtracking, and as well as the concept of the recursive algorithm, and as well as the iterative algorithm. So when you consider about the recursive algorithm, so within the case of the recursive algorithm, like algorithm, backtrack of K, and basically this kind of the concept of the algorithm describes the backtracking process using the recursion. And on entering the first K minus 1 values, that is here you can observe for each x of k that belongs to the tree of of x of 1 comma x of 2 comma till x of k minus 1 do, and check if the bounding function on k on the items that you have considered, that is x of 1, x of 2 and so on till x of k, which is not equal to 0, then check whether if x of 1 comma x of 2 etc till x of k is a path to the answer node. Then write such kind of the items, that is what are the items that you have taken into the solution. If k is less than n, then backtrack, that is not the possible solution. Then in such cases, that is backtrack of k plus 1 to the previous level. So this is where we can apply the backtracking concept using the recursive algorithm. So recursive algorithm is been implemented, that is further once again you are calling to the same kind of the function, that is backtrack of k plus 1. So here the classic example that can be given for the backtracking is related to the 8 queens puzzle that asks for all arrangements of 8 chess queens on a standard chess board. So we'll be prompted for the a number of the queens which are being provided, where you need to arrange these kinds of the queens such that no two queens are under attack simultaneously, that is beside. And similarly within the same row and within the same column, the queens cannot be present. So here the classic example that can be given is the 8 queens puzzle problem that asks for all arrangements of the 8 chess queens on a standard chessboard so that no queen attacks any other. In the common backtracking approach, the partial candidates are the arrangements of the k queens in the first k rows of the board, all in different rows and columns. Any partial solution that contains 2 mutually attacking queens can be abandoned. That is, in such cases, you have to backtrack and find any other path that can be lead to the solution. So here, this kind of the algorithm describes the backtracking process using the recursion, because it is a recursive algorithm, and on entering the first k minus 1 values, that is x1 comma x2 comma etc till x of k minus 1 of the solution vector, x of 1 to n have been assigned, and x and as well as the n are the global kind of the variables that are being used in the algorithm. And coming to the iterative algorithm, that is algorithm I'm using the I backtrack of n, and initially we are providing the value of here the k to be equal to 1 and repeat as long as k not equal to 0. If there remains an untried x of k that belongs to the tree of x1 comma x2 comma etc till x of k minus 1, and bk of x of 1 comma x of k is true, the bounding function is true, then if x of 1 till x of k is a path to an answer node, then write those kinds of your the items into the solution set, that is x of 1 to k, and then increment the value of your the k plus k equal to k plus 1. That is, consider the next state, and else if the above condition fails, then k equal to k minus 1. That is, you have to move back to the previous set to find whether that kind of the path leads to the solution or not. So observe the difference between the recursive path and as well as the concept of your the iterative part. So within the case of your the iterative path, that is, if there remains any untried set of the values which belongs to the tree T, and if also the condition, that is constraints are being satisfied, then you can take that kind of the path into the answer node. And if at any case if it is not being found, then in such cases backtrack. Apply the concept of your the backtrack, that is k equal to k minus 1, which denotes the backtrack to the previous set. So within the iterative algorithm which describes the backtracking process, all the solutions are generated in x of 1 to n and printed as soon as they are being determined. And if you observe, that is, we are starting from the initial level, that is k equal to 1, and while k not equal to 0, that is do. If there are any untried elements which are being present, which belongs to the T, and also the criterion is being satisfied, that is the bounding function is being satisfied, then you can take that kind of the path, that is x of 1 to x of k, into the answer node. If not, then in such cases, that is here you need to consider about this kind of the k equal to k plus 1, which indicates you need to consider the next set of the values. And even if this condition fails, then you have to backtrack, that is, apply a backtrack to the previous set. And the most classic example to solve the problem of the n queens problem, is the concept of the n queens problem. So within the case of the n queens problem, the problem is to place n queens on an n by n chessboard so that no two queens attack each other. No two queens are under attack by being the same row in the same column or on the same diagonal. Given n chess queens, place them in the chessboard of the size n by n so that no two queens attack or eliminate each other. A queen can only attack if another queen is either on the same row or the same column or the same diagonal. So the concept of the n queens, like what is this actually the n queens problem? Given n by n chessboard, n by n size chessboard, and consider the value of the n to be equal to something like a 4 to start with. That is the board which contains this is the 4x4 chessboard, and you're also familiar about the chess coin, that is queen, pawn, and so on. So the queen has to be placed in the n by n chessboard. There are 4 queens, that is q1, q2, q3, and similarly there are 4 queens that are present. And coming to the concept of the 4 queen problem as initial state to start with, or is actually the 4 queens problem. So within the case of the 4 queens problem, you have to arrange these kinds of the queens such that no two queen are under attack. The constraint that has to be satisfied is no two queens are under attack. What does this mean? That is, here if I place q1 here, to start with. Then in such cases, you cannot fill Q2 in the same row and in the same column. And as well as we cannot place the next queen in the same diagonal. What does this mean? That is, if I place queen 2 in this scenario, then these two queens will be under attack. So that is not the solution. Similarly, I cannot place Q2 in the next one. This is also not the solution, because these two queens will be under attack. That is, it should not be within the same row, it should not be within the same column, and it should not be within the same diagonal. So here, if you place queen 2, this is also not the solution, due to the reason like these two queens, queen 1 and queen 2, will be under attack. And similarly, you cannot place queen 2 in this cell, because queen 1 comes under attack with the queen 2. Similarly, can I place the queen 2 in this cell? We cannot place queen 2 in this cell, because these two queens will be under attack. And can I place queen 2 in this second cell of, second row, the second column, second cell? Then these two queens will be under attack. So we cannot place these two queens in this order. And what is the next possible path? The next possible path that you can arrange is, you can place queen 2 in this cell. As of now, the constraint is been satisfied. What is the constraint? No two queens shall be placed within the same row and within the same column and within the same diagonal. So if I place a queen 1 here, and if I place queen 2 here in this cell, these two queens are not under attack. That is one of the possible solutions. So queen 1 we have placed and queen 2 we have placed, and in such way find all the queens which can be placed in this n by n chessboard, such that the solution can be obtained by satisfying the respective conditions. And take the next scenario, like take for example queen 3. Can I place queen 3 in this cell? We cannot place. Why? Because these two queens will be under attack. When the two queens are under attack, that is not the viable solution. That is not the solution that has to be taken. And take the next one. That is, can I place queen 3 in this cell? Queen 3 cannot be placed, because these two queens will be under attack. That is how we can say this is not the placement of the queen 3. Now, can I place queen 3 in this cell? We cannot place. Why? Because the diagonal. That is, these two queens will come under attack. That is queen 2, and similarly queen 3 will be under attack. And that is how we cannot place queen 3 in this cell. Can I place queen 3 in this cell? This is not the correct placement, because these two queens will be under attack. And similarly, can I place queen 3 in this cell? We cannot place in this cell, because the diagonal, that is queen 2, comes under attack with the queen 3. That is how we need to backtrack. What is the concept of the backtrack? If it leads to the solution, then move to the next level. If it does not lead to the solution, then backtrack and find the other paths which are been available. So we have started, that is from the root, we have took, that is queen 1 in the first scenario, and then in what are the other other paths which are been available? That is, you can take queen 2, you can take queen 3, and you can also take queen 4 in the next scenario. If you take q1, then that is, you can take queen 2 and similarly queen 3, and the next one, that is queen 4. These are the state space tree diagram. So I placed queen 1 as in the first cell, first row, and the queen 2, that is queen 2 is being placed in the second row, third cell. So when I place queen 2 in the second row, the third cell, these two comes under attack. Then what should be done? So here if you place the second row and the third column, then this is the solution. because these two queens are not under attack. Now the next scenario is where to place the queen 3. So queen 3 cannot be placed in this cell, 3-1 cannot be placed, 3-2 cannot be placed, 3-3 cannot be placed, and similarly 3-4 it cannot be placed. So queen 3, there is no place to fill. So in such cases, backtrack. What does this mean? That is, backtrack to find the alternate paths. What are the alternate paths, other paths which are being available, or untried paths which are available? That is, here you have placed queen 1 in the first one. There are no problem. The constraints is been satisfied. And when you place queen 2 in the third cell, no constraints, it has been satisfied. This is your first position, second position, third position, and similarly the fourth position. And similarly, when you place queen 2 in the initially, I'm repeating once again. So here, a queen 1 is being placed in the first cell. So queen 1, there are cells like 1, 2, 3, 4. Queen 1 you have placed successfully, no issues. And when you place queen 2 in the second cell, this constraint problem has been involved. That is, queen 2 cannot be placed in this cell. So when queen 1 is being placed in this first cell, you cannot place q2 in the second row, second column. And similarly, queen 3 can be placed here in the 2-3, that is second row, and similarly third column. When you place this one, that is, when you place q1 in the first row, then we cannot place queen 2 in this cell, and we cannot place queen 2 in this cell. And if you place queen 2 in the second row and similarly third column, it is satisfied. And how about the next queen? That is, next queen, that is queen 3 cannot be placed here, queen 3 cannot be placed here, queen 3 cannot be placed here, because these two queens will be under attack. And queen 3 cannot be placed here because these two queens will be under attack. And we cannot place queen 3 in this cell because these two queens will be under attack. Then in such cases, move back, backtrack and find the other possible path. What is the other possible path? That is, where can I place queen 2? If I cannot place queen 3, then I can place in this cell. So queen 2 can be placed in the 2-4, that is second row, and similarly fourth column. Then further, once again, find whether can I place queen 3, whether I can place queen 3 in 3-1, we cannot place. Whether I can place queen 3 in this cell, we can place, because no two queens will be under attack as of now. So I can place queen 3 in this kind of this cell, because no two queens will be under attack, and similarly it is not in the same row, it is not within the same column, and it is not in the same diagonal. So can I place queen 4? Because we have finished about, so far we have finished queen 1, queen 2, and similarly queen 3, and take the queen 4. Queen 4 cannot be placed in this cell because these two queens will be under attack. And queen 4, if I place here, these two queens will be under attack. I cannot place queen 4 because these two, and similarly, these two queens will be under attack. Queen 4 cannot be placed here. And if I place q4 here in this case, that is, these two queens will be under attack. And similarly, if I place queen 4 here, then these two queens will be under attack. So what can you interpret? You can interpret in such a way that if I place queen 1 in the first row, first cell, so if I place queen 1 in the 1-1, that is first row and similarly first column, that is here, if you consider the chessboard, if I place queen 1, I cannot place queen 2 here. I cannot place, I can place here q2. If I place q2 here, then there is no way of placing the queen 3. And that is the purpose where we are moving to the next part. path, that is place the q2 in 2 4. If I place q2 here, q3 cannot be placed here because q1 and q3 will come under attack. And similarly, can I place q3 here? Yes, I can place, because no two queens will be under attack. And similarly, I cannot place q4 here, you cannot place q4 here, I cannot place q4 here, and similarly I cannot place fourth queen because these two queens will be under attack. I cannot place q4 in this one because these two queens will be under attack, and I cannot also place queen 4 in this scenario because these two queens will be under attack. So that is the purpose where move backwards. What is the backwards path? That is queen 3 at any case you cannot place, and q2 is fixed here, and when you place q2 here, we found that there is no place for the q3, and that is the purpose where we have moved to the next path, that is q2. When I place q2 here, there is no path for you on the q4. So in such cases, move back and place the queen 1 in the next path, that is choose another path by placing the queen 1 in the second first row, the second column, and find whether we leads to the solution or not. That is how the backtracking concept has been involved.